Okay, I'd like to speak about a story which I call the doubling population. Code for this story is available here at these One on Epsilon videos repository. I initially created this material for some 2022 workshop in Melbourne together with Elizabeth Roche. So let's play with a very simple scenario with just a few mathematical models. And the purpose of this scenario is not just to explore the models, but also to see some Julia syntax for using these models. I won't get all the way through this notebook, but will rather just go through the first example and perhaps a second, and then just present an overview of what there is. So from a modeling perspective, let's take something very, very simple. Let's assume that we believe that we observe that every day our population doubles. Okay, so every day our population doubles. Now, if I tell you every day the population doubles, you can have multiple models, multiple mathematical models that will describe this. This is one such model. This is a model where x of t is the size of the population at day t, and then you multiply x of t by alpha, with alpha being 2, and that's going to be x of t plus 1. Okay, so that's a doubling of the population. Now, the thing is that this is not the only model which describes such a scenario. There are different models of various levels of complexity that describe a doubling population, and that's kind of the theme of this story. So at least I identified kind of six separate models, and some are deterministic, some are stochastic, some are discrete time, some are continuous time, and these models handle a doubling population. So I guess that from a modeling point of view, the take-home message here is, well, even though you have a simple description, the population doubles every day, there's not necessarily a single model to do that. But let's play a bit with Julia and see the first example of this, and then just kind of highlight the other examples. And you can explore this notebook yourself for the other examples if that's interesting. So in this case, all of the code we have is in an environment that you can download, and the PKG package is just a way to activate environments. Okay, if you were working in the REPL, then you'd use the package manager mode for that. If you're running this for the first time, you might also want to do package.instantiate, just to kind of see what we do here. So if you do package.status, then these are the packages associated with this specific environment. Okay, so we're going to use a few of those packages: plots, differential equations, distributions, random is inbuilt, data frame, CSV, statsbase, and data structures. We won't use all of those for that first example. And in fact, in the first example, what we want is we want this alpha constant, this alpha, okay, I just called it alpha constant, but this alpha to be 2, we're not going to deal with kappa constant for the first example. Of course, in Julia, you can do things like backslash alpha tab, and that creates the alpha Unicode character. Okay, so for the purpose of this demonstration, things will look at first a bit more complicated, but the reason for doing it so is that it'll also work with output of differential equations.jl. So we're going to create our own structure where we keep the model trajectory. Okay, so a struct in Julia is kind of like a type or a class if you would like. Okay, but it's really a type. And this structure has two variables, which we call with very, very minimal names. T is the times and U is the state values. These are what they are. And this here, this multi-line string, is the doc string for that structure. So if you run this cell and do question mark on the name of the structure, which we call model's trajectory, now types in Julia have uppercase for the first letter. Okay. So we say that's a generic structure that represents a model trajectory where T, you see this T is presented like here because it's in Unicode here. T is treated as an indexable object of array, and U is indexable object of the array of the values of the trajectory. So times and values. Okay. So here is our function which creates a model trajectory for this model one. Okay, it's not a very complex function. Let's look at it. So model one trajectory, this function does not have any positional. arguments. So this is where we would have put positional arguments. It only has keyword arguments after the semicolon. And the first keyword argument or a keyword argument, Tmax, is just going to be the default Tmax as a default value. Okay, and that's going to be 7. And if we run the function with something else, we'll say Tmax equals something else, and it won't be 7. And x0 is your initial state. Well, how many items or individuals do we start with in this population? Well, we start with 1.0 individuals in this population. So a trajectory here is going to be really the state trajectory of this population. And the way we do so here is we initialize it ahead of time. And we say if we're going to run from times 0 to 7, then it needs to be of length 7 plus 1, Tmax plus 1. And we initialize it as an empty, undefined array. This is one way to initialize an array in Julia, and this is an array of float 64s. So here we have our initial state. So our state is x is going to be x0, and then you put this x into trajectory 1, this kind of, set the initial state in the trajectory. And then we're going to loop Tmax more times. So, and because indices in Julia start at 1, then T is going to go here from 2 until Tmax plus 1. And each time, this is really the model dynamics, we'll take the state and we'll multiply it by this alpha const. So in this case, these are the model dynamics. Okay. And then we'll put the state in the teeth index in trajectory. And finally, here we construct a model trajectory. And this constructed model trajectory has for t times from 0 to Tmax. And the trajectory is just the trajectory that we had. So if we run the cell here, if I, for example, comment this line here, then we have a model trajectory where these are the t values and these are the u values. But you can also inspect the fields by taking traj1.t and traj1.u. This comma presents this as a tuple, and here are the values of the model trajectory. Okay, now let's also speak about interpolation. And let's create a function which gives us the value at any time, not just at integral days, day 1, day 2, day 3, day 4, etc. Let's speak about any time which is a real value. So this says that time is of type real. Okay. And MT is an object-like model trajectory, which is assumed to have types T and U. So what you see here is we didn't specify the type of this MT, but by having such a function, we assume that we can do mt.t and mt.u, etc. So anything you give here that you could apply .t or .u that has a t and a u would work under such a value at time function. So let's start with some error checking. We first do checking to see that the time is not before the first time in the model trajectory. So the way this construct works is if this would have been true, then this would have also been evaluated. And in this case, this would throw an error. So this is short circuit evaluation. So if this is true, then we are in trouble and we have the time precedes trajectory. And then let's find the first index of the time where the time is greater, the time of the model trajectory is greater than our given time. Okay, so I is going to be the index of the first time greater than time. This is a Julia anonymous function, and we hence went through our times. Our times are going to be, for example, 0, 1, 2, 3, 4, 5, 7. 3, 4, 5, 6, 7. And if we had, for example, a time 6.5, then I would be the first index in this unit range, treating it as an indexable array where we are not less than time. Now, if we didn't find such a time, that means I equals nothing, then we must be in another error case. That means that the time exceeds the trajectory. So if we would have put 7.1, we would get this error. Now, once we've done that, then we can take T1 and U1 to be the time that we found, so the first time that exceeds the value, and the first state that exceeds the value. And if we actually happen to have an exact match of that time, so if we put in this case like an integral time, then we will return that time. Okay. Otherwise, we'll continue. Now, if we're down the road, if that has not happened, if we did not fall on this error, did not fall on this error, and did not return that time, then that means that I must be greater than 1. We can assert that just to be sure. And then the previous index is going to be I minus 1. Now, then we can take the time at the previous index and the state value at the previous index. And finally, with this, we can interpolate and we can say, okay, our returned interpolated value is the value of the previous index plus a slope, which is the difference in state between the current time u1 minus uprev over the difference of times multiplied by that kind of fractional time, time being between time and tprev. So this is in a sense a generic interpolation function, and we'll see how it works in a second. So once I run this, then we have this function, and let's see how we can plot this. So let's get a plotting grid from 0 at steps of 0.01 up to default Tmax. So that's going to be a plotting grid. Let's take the trajectory one on grid. So this is going to be a trajectory much finer than the time 0, 1, 2, 3. There's going to have 100 steps per time interval. Okay, and we do this Julia comprehension where T1 is going to run on all values in this grid, and we get from the trajectory the value at this T1. Okay. Now the plot, all the plot does, we're doing 2 steps of the plotting. The first element is going to be a scatter plot. So if I was to, for example, turn this off and run it, then we just get a scatter plot. And this scatter plot has the value, the times of the trajectory and the values, color red, legend, etc., a few things. If we add a second plot, and we can do this by P2 as plot on P1, and we plot with T-grid, and this is the trajectory one on grid, then we have the continuous interpolation. So there we go. This was our model 1. You could have said, oh, model 1 is a discrete time model, but if you want to treat it as a continuous time, and if this is your model, then what you're assuming that happens between days, then you can go with this kind of linear interpolation before days. Of course, there are other ways to do interpolation. So now, the nice thing is that this is not the only model for doubling at any time t. Here's model 2, which is differential equation model. So this model means that the derivative of the population size at time or day t is going to be some constant times the population size. Now it turns out that if that constant is log alpha, or more generally or more specifically for alpha equals 2 log 2, which happens to be this value 0.693, then this model also describes doubling of the population. So just to see this happen, let's now go here for model 2. And here we could have used we could manually try and solve this differential equation. It's not a difficult thing. I mean, it even has an explicit solution, which is an exponential. And of course, this exponential just passes through these points. But in this case, let's actually use the differential equations package. So let's use an ODE solver. So in an ODE solver, what we need to do is we need to define a right-hand side function, which is a function of your state, of your parameters, and of your time generally. In this case, the right-hand side function is just going to be this kappa const times your state. So it doesn't really consider the parameters or the time. So as you can see, we've defined kappa const to be this log 2. Okay. Log by default is the natural log. You can do in Julia log 10 and log 2, etc. But here is a natural log of 2. So the ln of 2, if you would like. Okay. Then an ODE prob is an object which has the right-hand side of the ODE, the initial value, and the time horizon. And the ODE solution solves the ODE prob, and here we're giving the type of solver and a few other parameters if we would like a few more keyword arguments. Let's return the ODE solution. So this is how we get a Model 2 trajectory. Now, notice that if I do traj.t and traj.u, so let's just do traj.t for a second. Traj.t, these are times which I get in the trajectory. And the ODE solver decided at what points it should give me times for the trajectory. And this is the state values, which are of the same. So look, there's 62 elements of the state value. So we started at 1 and we got to roughly 128 up to some numerical error. Okay, just like the first trajectory. So that's how we get the trajectory. And if you want now, then we could still use our interpolating function, but this interpolation will be on the values of the ODE trajectory, so it will be finer than what we see here. Okay, so our interpolating function on this trajectory at times t1 for t1 and t grid, and it's the same t grid, and we do a plot. And finally, we see that this is model number 2. Right. So model number 1, which was a discrete time model, is really just those kind of red dots. Model number 1 interpolated has linear lines between or straight lines between those dots, whereas model number 2 ODE is a continuous exponent that grows between. So you can continue with this notebook. I won't continue with this video much longer, and you could see that there are further and further models. And let's just now not discuss the Julia code, but just ideas of the models very briefly. So the third model is a stochastic model, but this is a discrete time stochastic model. So now x of t is a stochastic process. It's no longer a deterministic process that just evolves depending on its history. It's a stochastic process. In this case, it happens to be a Markov process as well, a discrete time Markov process. You can call it a Markov chain if you would like as well. Now, in this case, x of t plus 1, we say that all the individuals at time t, individuals 1 to x of t at time t, each had their offspring. And their offspring of individual I at time t is going to be this random variable psi it. And we just want the expectation of this random variable to have 2. This is also a branching process, if you would like. So the number of this random sum, which is a sum of a random number of random variables, is going to be what we get in the next time instance. If you want to look at a trajectory of this model, let's go to a model 3 trajectory. The point here is that I won't go into the code at this point, but from time t to t max, what we're doing is we're having offsprings. So we're doing a random from this distribution, and a distribution, we can choose it to be Poisson by default, but it can be anything else. So you can put other distributions. You just want that this distribution will have a mean of 2. Okay, so how is that done? So let's see, dist by mean generator. So this function, dist by mean generator, where did I define that? Um, Sorry, so this is the alpha const. Okay, so it's a Poisson with a mean of 2. Okay, so this is by default, but you could have given a different function here for the distribution where this function needs to get kind of, hey, you give me the mean and give me a distribution that will have a mean of 2. There are many types of distributions with a mean of 2. If you just do Poisson, you actually get a Poisson distributed with a mean of 2. Now, what we're doing here is we are summing the offsprings of such random instances, and that's what happens. So if you look at a trajectory, let's run a trajectory of this. So here is one trajectory, and notice that every time that I run this again, I get a different trajectory. Okay, so I'm going to run this again and again. I'm going to get different trajectories, and these are stochastic trajectories. We can now repeat these, for example, 1,000 times. We get 1,000 random trajectories, and these are runs of these 1,000 trajectories. Okay. Now, we could still do the mean of each of those trajectories, and here we can look at the scatters of those means of these trajectories and look and see that the means are on average doubling. And if you do 1,000,000 trajectories and not just 1,000, you'll see that the means fall exactly on the doubling. So that was model number three. Now, if you go to model number four is kind of like model number two, but you're also adding some random noise. So this is really a stochastic differential equation, and that's going to be model number four. Whereas model number five is a discrete state, but continuous time. So that's a continuous time Markov chain. And this means a transition of a continuous time Markov chain at rate kappa times x, where again, kappa is this number. So let's look at four and then at five very quickly. So here is model number four. Now for model number four, we will use the SDE problem, which is from differential equations.jl, and we'll solve this. That's using differential equations.jl and get trajectories. And we can get all kinds of trajectories. Okay. And it turns out that we want model number four with constrained means. This is these, sorry, with constrained means. This is these purple trajectories. Okay. That's model number four. And for model number five, what we're going to do is we're going to do a Gillespie algorithm pretty much. So that's a continuous time Markov chain. And this is what a trajectory of it looks like. Okay. So the population, do you see the population doubling? Not per se, but on average, it's doubling. And if you have many of these trajectories, again, just like the discrete time case in this continuous time case, they're doubling on average every time unit. And you can see this once you do the average of everything, that the averages of all these models are doubling again. So this is one trajectory of a doubling population. Here, let's run this again and again and again. Each time we get a different uh, trajectory. Oh, sorry, we're getting the same one because we have the same model, the same run. So every time I run this, I run this and this, I'll get a different trajectory. And I run this and this, and I get another different trajectory. Run this and this, get another different trajectory. We have an ensemble of such trajectories. On average, they are doubling. Okay. And here's even a way to do an animation where the number of realizations of the model increases from 10 to 10,000. And what we're getting is the means. And of course, on average, these models, as you get to 10,000, get very close to the deterministic doubling case. Okay. Now, the sixth model is different, and that's an agent-based situation. And I won't speak about this further, but basically, the times now between events are not necessarily exponentially distributed. The model is not necessarily Markovian, and this model is more complex, and I'll let you investigate that on your own. So that's this last type of model. Now, an interesting thing with this last type of model is that if you do not use an exponential distribution, then you won't actually get a doubling. So the thing is that if you want a doubling and you want a distribution which is, say, not exponential, say uniform, then you actually need to adjust the distribution. And a challenge which I leave to you if you're actually going to go through this notebook is try to calibrate model 6 so it behaves on average like the other models. Okay, so that's what we've had here. There's quite a lot of code, but it's all around a very simple problem. The problem is how do we describe a doubling population? a very simple model, a slightly more complex model, a stochastic model, a continuous time stochastic differential equation model, a discrete state continuous time model, and a non-Markovian agent-based style discrete event simulation model. Different models for the same thing, and hope that you got something from these Julia examples as well. Okay, thank you.